By far the most important distinction between types of data that we deal with in machine learning is that between data that we have and data that we don't have, at least not yet. Almost always, the latter is what we're ultimately interested in. It's the application that we're going to put our model to in the end. But we don't have it yet, and the future is unknowable, so we have to make do with the data that we've got. We're going to assume that the data that we have is representative of the future data. If that's not the case, then we're already in trouble. We're going to need to use the data that we have for training, but if we use all of it for that, then we'll have no way of testing our model. It's important not to test the model on data that it has seen already. That basically doesn't qualify as a test at all, because the model already knows the answers. Not all of the models that we deal with in machine learning have the capacity to memorize all of the data that they've seen in training, but some do, and it's generally a good idea to just assume that they all can. A model needs to generalize to unseen data, or it is essentially useless. If it can only operate on the data that it's seen in training, then really what is the point of it? This is, once again, the O word, overfitting, and as always, we really want to avoid it. To get around this, we split the data that we have into two different sets. We take some of it and reserve it to use for testing. So we have what's called a training set and a test set. The test set is put aside and never looked at. You only bring it out right at the last minute. Don't use it for checking that your code works. Don't use it for tuning your hyperparameters. If you do those kinds of things, then there is the possibility of information from the test set contaminating the training process and invalidating your tests. Obviously, there is a trade-off here. You need enough data in your test set to get meaningful test results, but all of the data that you move into your test set is data that you no longer have available for training, and that may impact the success of your training and the performance of your model. In practice, the amount of data that goes into the test set will vary according to the amount of data that you have and also the kind of problem that you're dealing with. But in practice, it's often of the order of 80% in the training set and 20% in test. So I've said we mustn't use the test set at any time except at the very final testing stage. But we often want to do things like checking that our code works and tuning our hyperparameters. We can't use the test data for these purposes because that may lead to leakage. And so typically we split out another chunk of the potential training data and reserve that for purposes like this, and this is known as the validation set. You can use the validation set for tuning your hyperparameters. But again, this is more data that is being sacrificed and can no longer be used for training. Typical splits here might be 70% of your data for training, 10% for validation, 20% for test. But again, it varies quite a lot depending on the problem. If you really don't have enough data to support a separate validation set, you can do something called cross-validation, where you divide up the training set into chunks, you train on all but one of those chunks, and then you validate against the other, and you do that for all the different chunks in turn. Then you average over the results. In the limit, the validation chunk can be as small as a single sample, so that you each time train on everything but one sample and validate against that sample, and you repeat that for all of the samples in your training data. Obviously, this can be very time-consuming, but it shouldn't be necessary to do that unless you already have very little training data. As indicated earlier, the model inputs X and the model outputs Y could be any kind of data at all. They might be numbers or text, but they might be images or sounds or video, or they could be all of these things in combination. For most models, the data will eventually be represented numerically. There are a few kinds of model that can deal with other kinds of data, but usually we'll be dealing with numbers. And we'll discuss ways of converting other things into numbers shortly. An important distinction between classes of data is that between continuous data and discrete data. So continuous data is real numbers and also things that are well represented as real numbers. For example, pixel values in images are in practice typically discrete. They are integer values in the range of 0 to 255, for example. But in practice, we will almost invariably treat those as real numbers. Discrete data is data that is in separate classes. We will usually represent these by integers without necessarily including all of the properties that we associate with integers, like ordering. Examples of discrete data would include things like truth values, presence or absence, general categories, words, letters, abstract concepts, and arbitrary symbols relating to things in the world. So things like amino acids in protein sequences or Disney princesses. There can be some grey areas in the discrete continuous dichotomy when dealing with ordinal data. That is data which has some natural sequence to its values. Things like star ratings out of 10 or clothing sizes or age bands. We tend to care most about this discrete continuous distinction when we're thinking about the output type of the model, because that affects our choice of loss function. If the output is continuous, then the problem is called regression, and a distance-based loss function is often appropriate. For example, a typical regression loss is mean squared error. If the output type is discrete, then the problem is called classification, and we may instead want to use an information-based loss. For example, cross-entropy is commonly used as a loss in classification problems. We'll go into details of what these things are next week. Both kinds of losses will often instead be conceptualized in terms of probability. But again, there's a similar dichotomy between discrete and continuous distributions there. When it comes to model inputs, a few models are able to deal with discrete or categorical variables directly, but in most cases, models will expect a numeric input. So it's important to have a way of converting between categorical and numerical variables. It is possible to assign numeric values directly to the different classes in your categorical variable, but this is often not a good idea because the relationship between the numbers and the categories will be completely arbitrary. In particular, the ordering and the relative scale of the different numeric values will have nothing whatsoever to do with your inherently unordered categories. Instead, it is common to split out the different classes into separate feature dimensions or indicator variables. So instead of having a single dimension representing, say, film genre with values action, comedy, horror, and so on, you would have a bunch of different dimensions, each of them representing only one of those things. So you would have an action dimension which is either 0 or 1 on the input, a horror dimension which is either 0 or 1, a comedy dimension which is either 0 or 1, and so on. We will often use notation like this to represent indicator variables. This is just a shorthand function saying if the condition in the brackets is true, then output on 1, otherwise output is 0. This is a very familiar concept computationally. It's a typical way of representing Boolean values. To represent whole categorical variables like this computationally, we will typically use a vector where each element represents one of the possible options, and all of them will be 0 except for the one which is true, which will contain a 1. This is known as a one-hot encoding. One-hot vectors are a simple example of an embedding, which is just a representation of one data space in another. Embeddings, or at least the terminology of embeddings, are particularly commonly encountered in natural language processing, where embeddings are used to represent words. A one-hot representation of words would have to be very large. You would need as many dimensions in your feature vector as there are words in your vocabulary. And moreover, it would impose an unreasonable degree of independence on the different values. Words in a text are not wholly independent from one another. They are related by meaning and by patterns of usage. A word embedding maps the discrete words to points in a lower dimensional continuous space, attempting to capture some of their semantic properties in the relative positions and directions between those points in that space. Such embeddings are typically learned rather than engineered, although they may be learned separately from the task at hand. A number of pre-trained word embeddings are available that you can use more or less off the shelf. There may also be cases where we want to convert from a continuous numerical value to a categorical one. There are several possible approaches to this. Probably the most straightforward and basic is thresholding, where you choose some threshold value, and if your numerical value is above that, then it is one class, and if it's below that, then it is the other. This obviously only applies to binary classes, but it generalizes straightforwardly via binning, where you have multiple threshold values dividing up the numeric space and assigning them to different classes. An alternative approach, which is sort of comparable to the one-hot vector case, is to have multiple predicted numeric values and then choose between them to assign the class. So, for example, you might do this by just choosing whichever one scores highest, or you might have multiple values and take a vote across them. So far I have discussed this as if your data is only a single type, but quite often you'll be dealing with collections of data that have lots of different types in them. Generally what we do with this is we just bundle them all together into an even larger dimensional space, which represents all of the different things in the set. It's useful to distinguish two special cases of collections of data. The first is images, or more generally digital signals, where you have a large number of data elements, but they're all the same type, and they are related to one another spatially or temporally. The second special case that it's useful to distinguish is sequences, where you have multiple elements and they may not be sampled uniformly, but the sequence in which they occur is important. This might be things like words in a sentence or notes in a piece of music, or things that might be related temporally or causally, like medical histories or other time series data, movie plot lines, or financial crises. Loss functions and learning algorithms are often sensitive to the relative scale of features and also sometimes to asymmetry. So it's pretty common to pre-process data to iron out those kinds of differences that might distort the learning process. Examples of pre-processing steps that are reasonably common would be centering, where you subtract the mean from your features and so they all become centered around 0. Normalization, where you rescale them into some range. A special case of normalization is known as standardization, which involves centering and also dividing by the standard deviation so that all of your features wind up having a mean 0 and a variance of 1. And sometimes an additional step known as whitening, which is applying a linear transformation to remove correlations between the data and turn the covariance matrix into the identity matrix. It may be useful to apply other transformations to your data as well. A particularly popular choice is a log transform, which magically turns products into sums and so can convert parallel relationships into linear relationships and also exponential relationships into linear relationships, which may be more suitable for your model. Other domain-specific transforms may be useful as well, depending on the kind of data that you're dealing with. For example, transforming rectangular into polar coordinates, or applying a fast Fourier transform to move your data into the frequency domain. One important point about pre-processing your data is that anything that you do to your training data at training time, you also have to do to your real data at test time. That means that if you're going to do things like standardize your data, you need to remember the means and standard deviations that you applied then so that you can do the same thing to your test data. We've so far tended to assume, at least implicitly, that we know what our y's are. That is to say, what are the outputs of the model, both in terms of the general kind of thing that they are, and also specific instances that we will use during training. If that is the case, then this is known as supervised learning, where supervision in this case means that you have something available at training time which will tell you whether you're right or wrong. Supervised learning is probably the most straightforward and understandable kind of machine learning. It's learning by example. But these supervisory values, the ground truth labels used in training, have to come from somewhere. And usually, ultimately, that will be from human effort. That means that it can be difficult and slow and expensive to produce them. Often we will have data and we won't have labels, and we would like to be able to learn something in that case. This is known as unsupervised learning. At first sight, this might seem like something of a tall order. How can we learn anything if we don't know what is true? In all forms of machine learning, we're looking for patterns and structure and regularities in the data. In the case of supervised learning, the labels make that very specific. They tell us exactly what we're looking for. So, for example, consider these pictures of cats and dogs. Having the labels makes it clear that we're trying to identify which of them are cats and which are dogs. In the absence of labels, we have to consider some other kinds of criteria. Now, as humans looking at these cat and dog pictures without labels, we still have a pretty clear idea of which are cats and which are dogs, and that might be a useful way of partitioning the data space. But if you have no idea what's a cat or what's a dog, you might look for other kinds of structure. For example, half of these pictures are in colour, half of them are in black and white, and so that might be a pattern that you can pull out. In the unsupervised case, in the absence of labels that tell us what we're looking for, we have to have some other constraints or heuristics that narrow down the search to particular kinds of pattern. What sort of structures are we looking for, and how many of them? Probably the two most common forms of unsupervised learning are clustering and dimensionality reduction, and these actually correspond moderately well to classification and regression in the supervised case. For clustering, we're still looking for classes, but they are classes that we invent according to the patterns that are in the data. In the case of dimensionality reduction, we're still looking for continuous relationships between variables, but again, we have to find them rather than being told what they are. Of course, we can't just make up any old thing. We actually want things that we invent to have some meaning to them. There are a number of other learning modes that hover somewhere between supervised and unsupervised, and all of them are in one way or another trying to mitigate the difficulty or impossibility or expense of acquiring detailed, accurate labels. In weakly supervised learning, you have labels, but they're not very good. So they may not be in very much detail, they may apply only to a whole bunch of things and you don't know which ones are important, and somehow you have to distill out the crucial bits of information that will allow you to do your classification, for example. In semi-supervised learning, you have a small amount of labelled data and a larger amount of unlabelled, and you have to learn to use one to enable you to learn more information from the other. Self-supervised learning trains a proxy task for which the data can be generated more or less automatically. An example of this is image inpainting, where what you want to be able to do is fill in missing bits of images, and so you create a lot of training data where you just delete bits of images and try and recover the bits that were in the image originally. One final kind of learning is reinforcement learning. This is one that we will touch on briefly towards the end of the module, but we won't treat in much detail. Reinforcement learning is a very different learning paradigm because there is no training data. Instead, there is a training environment, and the learning is undertaken by quasi-autonomous software agents which interact with that environment and see how it behaves. In some ways, reinforcement learning is the most intuitive kind of machine learning, resembling at least some of the ways in which we learn as human beings. Reinforcement learning is very often used for learning how to play games and for training robots how to interact with their environments. An important feature of these problems is that the environment is dynamic and it is changed by the actions performed by the agent. And so it is necessary to learn sequences of actions, not just a single answer. Reinforcement learning typically is performed in simulated environments because you need to be able to do a very large number of repetitions, much more than it is practical to do in the physical world in most cases.